So for today, we're going to do quite a bit of review and add a couple of new things in as well. So the first thing we are going to review are these three of the exponent rules. So the first one we talk about is the product rule. Remember, product is multiplication. And I'm going to come over here to this little example first. So if I have h squared times h to the sixth, I can easily expand. So if you don't remember the rule, h squared times h to the sixth, when I have all that multiplied together, I have 8 total h's multiplied, which is h to the 8th. So hopefully you can recognize 2 plus 6 is 8, and that's what I call our shortcut. It's the rule, our shortcut, whatever. Again, if you don't ever remember, start expanding and you can remind yourself. The next rule is the power rule, so that's when we have a power to a power. So again, if I expand this x squared to the third, I can write x squared times x squared times x squared. And remember my product rule, or think I have 2 here, 2 here, 2 here. So altogether, that's x to the sixth. So the shortcut would be that I can multiply 2 times 3. So x to the AB would be our power rule. Then for the quotient rule, if I ignore my values right now, my coefficients, I have x to the fifth divided by x. Again, I can look at that expansion, and hopefully you remember anything divided by itself is 1. So it pretty much disappears, and I'm left with this x to the fourth. So x to the fourth is what I have left. So the shortcut would be 5. Subtract 1 is 4. So x to the a minus b would be my shortcut. Also 27 divided by 4. So 42. We are not going to subtract these. These are numbers, and we know how to divide with our numbers. Hopefully it's obvious that 42 will not divide into 27. So I'm going to reduce that because I think they are both divisible by 3. I believe that's the highest number. 3 divides into 27 9 times. 3 divides into 42 14 times. So that would be my solution there. So why don't you pause the video, give the you try an honest try, and then you can unpause the video to check your answer. So for number 1, the first thing I notice is I have a coefficient here. I like to work left to right. So 1 times 2 would give me 2. Then I can look at my u to the fourth and my u to the second. So if I have 4 here and 2 here, I can add those together to get u to the sixth. And then the same here, I have v to the 0, v to the first. So I can add those together. 0 plus 1 is 1. You can write the 1 or not write the 1. And you may or may not remember anything to the 0 power is 1. So this one really is kind of not there. But here is our answer to that one. Here, so I have all of this stuff inside parentheses to the 4th power. So you can think of it like distributive property. I have y to the 4th, or we can think of 1 times 4 is 4, so that gives me y to the 4th. And then if I look at my x to the 4th, so there's 4 4s, that gives me 16 x's. All right, now we are dividing. And before I use my shortcut, I do want to illustrate something. So for this a squared, I'm expanding. Here I have a to the third, b to the second. So this would divide to be 1. This is 1. This is 1. This is 1. So what am I left with? I'm left with b over a. Now, if we use our shortcut, we are going to start with something a little different. So 2 minus 3 is a negative 1, and 3 minus 2 is a positive 1. So what we must remember here is that we cannot have a negative exponent, that the negative exponent means to move to the opposite side, and in this case, it would be the denominator. So that's how we get the answer of B over A. Okay, number 4 has everything in it. So the first thing I need to do is simplify what's inside parentheses. So 2 times 2 is 4. A to the 4th, there's no other A to the 4th, so, or A. B to the 3rd, I'll just rewrite that. Okay. Then I need to take care of my power to a power here. So remember, don't use the shortcut on your regular coefficients. This is 4 to the 3rd power. So 4 times 4 is 16. 4 times 16 is 64. Then I have 3, or A to the 4th to the 3rd. So 3 4s is 12. And then 3 3s is 9. And then I'm ready to divide my b's, so I end up with the 64 and the a to the 12th. 9 minus 2 is b to the 7th. So before we start simplifying radicals, it is very important that we remember our perfect squares. So over here in my little side of my paper, I'm going to remember 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, and 13 squared is 169. And that probably will be enough. And that's important because then I know that the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. That's the easier or the better you know your perfect squares, your times tables, the easier this is going to be. So a lot of people, when they're simplifying radicals, or a lot of teachers will teach to use factor trees, and there's nothing wrong with that. I just don't like it. I think they can get messy, and then you can miss some important parts, numbers, values, whatever. So I like to use factor pairs, and so I list all my factor pairs. So remember that, well, first factor pair is always going to be 1 times whatever your number is. You can also use division. 343, 2 doesn't work. 343 divided by 3, 3 doesn't work. Unless you know your times tables and you can do it. So I know that the factor pairs of 343 are just the one 343 and then 7 times 49. My next step is that I'm looking for the largest perfect square, which I know happens to be 49. So this is how I use it. I can now rewrite this as the square root of 7 times 49. And when I can do that, I can rewrite this as 2 separate radicals, 7, the square root of 7, times the square root of 49. So the square root of 7, that's prime number. I can't do anything with it. It's just the square root of 7. But I know that the square root of 49 is 7, and so I get my answer, or my simplified answer here, 7 times the square root of 7. For example number 6. Let's see. So the factor pairs for 20 would be 1 times 20, 2 times 10, 3 would not work, 4 times 5, and since I'm at 5, I know I'm finished. And then we have to look here. We have x to the third, so that's this many x's. Okay. For my factor pairs, 20 is not a perfect square, neither is 10 or 5, but 4 is, and 4 is going to be my largest. So I'm going to use this. So I have the square root of 4 times 5, and then my x's. So what's the square root of 4? 2. How many pairs or groups of 2 x's do I have? I have one group of 2 x's, so I can factor that out or simplify that out from under my radical. And then what do I have left? I have the 5 and this little x here. Those cannot be taken out, so those stay under the radical. All right, then we have the square root of this stuff, and whatever we bring out front, we have to multiply by the number in front. So I have the square root of 27. 1 times 27, 3 times 9, and that is it. So my largest perfect square is 9. So here's how we rewrite this. We have negative 3 out front times the square root of 3 times 9, and don't forget the n. So the square root of 3, I cannot simplify that. The square root of 9 is 3, so that's now out front. And then this little n, there's nothing I can do with that, so it has to stay under the radical. Now I can't forget the negative 3 that was originally in front, so I have to multiply those together. So my final answer is negative 9 times the square root of 3n. All right, now we're going to rationalize the denominator. Rationalizing denominators involves rewriting a radical expression as an equivalent expression in which the denominator no longer has a radical in it. Just like we can't have a negative exponent, we cannot have a radical in the denominator. If the denominator consists of the square root of a natural number that is not a perfect square, we must multiply the numerator and the denominator by the same number that produces the square root of a perfect square in the denominator. In other words, I have the square root of 5 here. I cannot simplify that square root of 5. So, but I can't leave the square root of 5 in the denominator. But if I multiply this by the square root of 5, that will help me out. And whatever I do in the denominator, I have to do in the numerator. So here is why. If I have the square root of 5 times the square root of 5, that gives me the square root of 25. Is the square root of 25, is 25 a perfect square? Yes, I know that the square root of 25 is 5. So that's why multiplying by that same number helps me get rid of it. Then 5 times the square root of 5 is just 5 times the square root of 5. So when I bring that over here, what happens is I can actually simplify more because 5 divided by 5 is 1. And this is my answer. Same thing here. The square root of 2 cannot be simplified. So if I multiply the numerator and the denominator by the square root of 2, I have negative 6 times the square root of 2. And then the square root of 2 times the square root of 2 is the square root of 4. So now I have the negative 6 times the square root of 2. I know what the square root of 4 is, 2, and now I can simplify again. So negative 6 divided by 2 is negative 3 times the square root of 2. And just so you know, you can never multiply a number that is not in a radical or divide into a number that is in the radical. It's two separate things. If you're not in the radical, you can't be put together. All right. If you would like to pause the video and try 4 and 5 by yourself, that'd be great. Otherwise, I will work those out. So I'm going to multiply by the square root of 3. So that's going to be 6 times the square root of 3. This is the square root of 9, which I know is 3. And then I can continue to simplify. 6 divided by 3 is 2. And then number 5, multiply both by the square root of 3. 2 times the square root of 3 is just that. This is the square root of 9, which is 3. This time, nothing can be simplified, so that is my answer. Okay, so radical expressions that involve the sum and the difference of the radical term, constant and radical term, are called conjugates. Conjugates are used to rationalize denominators because the product of a such pair contains no radical. So, for instance, what is the conjugate? It says the sum and difference. So what is the conjugate of 5 plus the square root of 2? It is 5 minus the square root of 2. And when we multiply conjugates, this is what happens. 1 times 1 is 1. 1 times the negative square root of 5 is the negative square root of 5. 1 times the square root of 5 is the square root of 5. And the square root of 5 times the negative square root of 5 is the square root of 25. So what happens here is I have a negative square root of 5 plus the square root of 5, which is 0. I have 1 here minus the square root of 25 is 5, which ends up being negative 4. So we can use this to rationalize the denominator when we have a two parts. So if I multiply this one by negative 4 plus 4 times the square root of 3, this is what happens. So I use distributive property here. 6 times negative 4 is a negative 24. And 6 times 4 times the square root of 3 is a positive 24 times the square root of 3. All right, down here, I have to multiply these two binomials. So I distribute twice. Remember, negative 4 times negative 4 is 16. Negative 4 times the 4 times the square root of 3 is a negative 16 radical 3. Then I come over here and I do the same thing. So a negative 4 times the square root of 3 times the negative is positive 16 times the square root of 3. And then negative 4 times positive 4 is a negative 16. The square root of 3 times the square root of 3 is the square root of 9. All right, so let's simplify this as best we can. This gives me negative 24 plus 24 times the square root of 3. This is a negative 16 times the square root of 3 plus 16 times the square root of 3. So again, that's 0. So the denominator has 16 minus 16 times the square root of 9, which is 3. All right. So we still have the numerator. And then we have 16 subtract 3 times 6 is 18, 48. We'll just scratch this example. Negative 24 plus 24 times the square root of 3 is 16 minus 48, which is, I believe, 32. So if we look at all of our coefficients here, they are all divisible by 8. So 8 divides into negative 24 negative 3 times. 3 and 32 divided by 8 is 4. So this is my answer. For this example, I am going to multiply the numerator and the denominator by 3. Change that minus to plus, the conjugate. And so now let's see what happens. Distribute. 2 times 3 is 6. 2 times the square root of 3 is 2 times the square root of 3. And then down in the denominator, I have 3 times 3 is 9. 3 times the square root of 3 is that. Then I have negative square root of 3 times 3. So that's that. And negative square root of 3 times square root of 3 is a negative square root of 9. Okay, so we have this in the top. And then I have 9. 3 times the square root of 3 minus 3 times the square root of 3 is 0. Minus the square root of 3 is 3. So my numerator is 6 plus 2 times the square root of 3. My denominator is 9 minus 3, which is 6. So I can simplify 2, 6, and 6 are all divisible by 2. So 6 divided by 2 is 3. 2 divided by 2 is 1. And 6 divided by 2 is 3.